Okay, we're gonna look at double integrals using polar coordinates. Well, why? We already did double integrals with rectangular coordinates. Do we have to move on to polar? And the motivation here is because some integrals are not integrable in rectangular coordinates. But if you change to polar coordinates, you basically convert everything. It is integrable. Yay, success. And then everybody's happy. So there's your motivation. And yes, you're going to be getting, not this coming week, but the following quiz and exams, I will give you an integral. I may not even give you a hint. I may not even say, oh, you're going to need to convert to polar. No hint, just like, here's an integral. And then you may start doing it in rectangular and then boom, you run into a brick wall. I can't do this. Or if you did have to do it, you'd have to do trig sub. No. What did I say about trig sub? Never have to use that in this course. Okay, I'm not saying you'll never use it in your future in some other math course. That could happen. Could happen. Okay, let's do a review of polar, shall we? Because I'm worried, some of you may have forgotten your polar. So here's the deal. Let's have this little over here. This is going to be the rectangular coordinate system that you already know and love. Okay, you know and love the rectangular coordinate system a lot. You got the x-axis, you got the y-axis, fine. And let's say you have a point P here in the rectangular coordinate system with the ordered pair x comma y, locating your point. Fine. Now, what about polar? Well, polar doesn't really have an x or a y axis, to be honest, but I'm going to draw one anyway, just to sort of locate ourselves in the world of polar, but they're really not there. They're not there. What does the polar coordinate system have? The polar coordinate system has a polar axis, which is the positive x-axis only. So I'll just sort of sketch it over here in pink. That's called, ooh. Bring it back. There we go. That pink thing is the polar axis, which is like the positive x-axis only. Okay. So the question is, how do I locate this same point P over here in the world of polar? We'll still call it P, but instead of x and y coordinates, you're going to have an R, which kind of stands for radius. You could think of it that way. And a theta, which is an angle. So, well, what's the R and what's the theta? Well, if you did draw a line segment connecting P from that point P to the origin, and by the way, there's no such thing as the origin in the polar world. It's called the pole, kind of like the North Pole, the pole. The angle that line segment makes with the polar axis is the angle that they're talking about here. The R you can think of as a length, but R can be negative, so we have to kind of be a little careful. Yeah, it's not always a length, but I like to think of it. I like my R's typically to be positive because I think better like that. So if you can, try to keep your R's positive, but they don't have to be. Okay, so how do you get from one system to the other? Because you may have to go from one to the other. Yeah. So in our world, you have to know both conversions. Okay, so let's talk about how do you get from rectangular to polar. So I'll give you a couple formulas. So for going from rectangular to polar, you already know your x and you know your y. Okay, so over here, and by the way, if you forget these conversions, they're very easy to rederive if you know the Pythagorean theorem and you know a couple of trig formulas, you'll be fine. If I drop a perpendicular down here over in the world of polar, where I think of this leg being the y and this leg being the x of this right triangle, I hope you can see that x squared plus y squared is going to give you r squared by the Pythagorean theorem. And so r is the square root of x squared plus y squared. Okay, fine. Now, what about the angle theta? Well, if you look at the fact that you already know y and x, and the trig function that comes to mind when you know the opposite and the adjacent is tangent. Tangent is equal to y over x. If you take tangent inverse of both sides, you'll get tangent inverse y over x. Will give you your theta. So those are the two conversion formulas to get from rectangular over there to the polar world. But what if you have to go backwards? Because you might. What if you are starting here in the polar world, so you have your r and you have your theta already? How do you get your x and your y? Again, use some of your trig and algebra knowledge. So you know your r, you know your theta. If I drop a perpendicular here, okay, you want to get your x and you want to get your y. You're just going to use trig. You're just going to use trig. So if you remember that cosine theta is equal to adjacent over hypotenuse, so in our case, cosine is equal to x over r. When you solve it for x, multiplying both sides by r, you get one of your conversion formulas. X is equal to r cos. And then using the fact that sine of theta is your opposite leg over your hypotenuse. So for this, we have y over r. Solve it for y by multiplying both sides by r, and you have your other conversion formula. So these are the two conversion formulas to get you from the world of polar back to rectangular, and then you have the other two conversions to get you from rectangular to polar. Voila, there's your review. We'll do a little bit more, don't worry. You're not ready to do double integrals yet. I'm going to do some preparatory work. Let's talk about sets or regions in the world of rectangular and polar and how you would describe them. So let's say you had a quarter of a circle centered at the origin here in the first quadrant, say. Look at that region. That's kind of cool. Well, in the world of rectangular, you would describe this using set notation as all ordered pairs x comma y such that, and this curve has the equation x squared plus y squared equals 4. You want x squared plus y squared less than or equal to 4, and then you also want x greater than 0 and y greater than 0 since we're in the first quadrant. And we're done. That would describe the set of all the points in this region. Now, if I describe this region in the world of polar, I'm still going to use the curly braces and the set notation. It's going to be all ordered pairs r theta such that, and then this is the part that's cool. Theta is going to go between 0 and pi halves. But what's r doing? Now you have to be careful because r blooms outward. So like if you look at graph paper for the world of rectangular, it's a collection of little rectangles. If you look at polar graph paper, which is pretty cool, it looks like a collection of concentric circles and rays. This is what polar graph paper looks like. Kind of like a spider web. Oh, this is perfect for Halloween. Great. So this region starts when r is equal to 0, and then it blooms, the r kind of blooms, it keeps growing out, more. Oops, I wanted a different color. Different color. Kind of blooms out, 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 and then the biggest radius we get is a 2. So r has a range of 0 to 2. And so this would be the set notation describing the same region, but describing it using polar. Well, so what? Well, what I want you to look at with these two curly brace notations is that the r and the theta, their limits are all pure numbers. Whereas it's not really true for x and y. Like if we did write this as an iterated integral, you could have it where x goes from 0 to 2, but then when I put my little man in there vertically, my y would go between 0 and positive square root of 4 minus x squared. That would be the limits on a double integral. Kind of yucky. Whereas the limits for a polar double integral will be all pure numbers. Nice. That should give you some motivation right there. Another really cool region that's perfect for polar is donuts. Donuts. They call these annular regions, okay? So in the world of rectangular, if we have circles with radii 1 and 2, you could describe using rectangular, this is the set of all ordered pairs where x squared plus y squared is greater than or equal to 1, but less than or equal to 4. I'm just shading in the region. It's a donut. But in the world of polar, it's better because you would do all the ordered pairs r theta such that r ranges between 1 and 2, that's the radii of those circles, and theta does the full 360 or the full 0 to 2 pi, and we're done. Now, both of those regions I just sketched, if any time you are doing a volume or setting up a double integral where your region is a circle or a part of a circle, like donuts and so on, or a quarter of a circle even, it's probably going to be a good idea for you to convert to polar coordinates. It's most likely going to be the case. All right, that's your red flag, like, don't stay in the world of rectangular coordinates. Get out, get out. Wawooga, wawooga, leave. Let's do a quick derivation of all this, and then we'll get to some more examples. So the idea of polar is you may not have a perfect portion of a circle. You have what's called sort of this generic polar region, and they call them polar sectors, where r may be arranged between a pure number to a pure number, but it may not. You'll have your angle go from something to something. So here's a portion here, some region, and that definitely is a polar sector. Okay. What is the area of one slice out of a circle? Anybody know? In other words, what's the area of a slice of pizza? In case you don't know, let's derive it. Let's do an area of a full pizza first. So let's say that this is a full pizza. I don't know if you guys are pizza fans. I know my husband is, but if you had some radius r here, I hope you know that the area of this whole circle would be pi r squared, right? True. Now, what angle is subtended by the entire circle? The circle subtends 2 pi. But in the area formula for a circle, you're only seeing half of the angle that's subtended. That's going to be helpful. Because in the world of pizza slices, let's say your pizza was a radius r pizza, the area is going to be, if your angle here was theta that you were subtending, half of that theta times r squared. And that's the area for a slice of pizza. And we're going to use that in my derivation here. So let's say you had some g1 function, and this is going to be, some function of theta here, and some other g2 here of theta. And then you're going to have this region here, you want to find the area of, or that's your region of integration. Partition it up into a bunch of little polar sectors. Those aren't rectangles. They kind of look like rectangles, but they're not. They're like polar sectors. They're sort of pseudo rectangles. So that's going to be called our inner partition. We're going to name it delta, and the norm of the partition is the length of the longest diagonal of one of those little itty bitty polar sectors. Now, what's the area of this? And what I want to do now is sort of consider, instead of that, what if we had to, let's go back to our slice of pizza. What if you had to figure out this area here, which is sort of looking like this area here? So what, and let's say you had an outer radius, we'll call it, you know, R, and then you had an inner radius, little r. So I claim this region that I have shaded in, the area of that, area of, we'll call that Ri, would be area of the outer pizza slice minus the area of the inner slice. If you don't believe me, let me walk you through it. So the area of the outer slice is the entire slice, that whole pizza. But we're going to cut out the area of the smaller pizza right here. If we cut away this red, what's going to be left? What's going to be left is the area that we want, just right there. Now, what about the angle here? So we'll call this delta theta, where let's say this angle here was some theta 2, and then you know, the other angle was some theta 1, and so delta theta is just going to be the difference of the thetas. But it's easier if we just call this delta theta. So now let's do the area of the outer slice. So watch what happens here. This is one of my favorite lectures, by the way. You'll see why in a minute. I don't want to give away the secret. 1/2 big R squared delta theta. Well, where'd you get that? From my area of a pizza slice, where our angle is going to be a delta theta. Minus the inner pizza slice, and that's going to be 1/2 little r squared delta theta. Now I'm going to factor out a common factor. It looks like both of these pizza areas have a 1/2. So by the way, I'll call this area delta area. I'm going to factor out the 1/2. And then I'm going to have big R squared minus little r squared, and then delta theta, I'll factor him out too. Okay, so now what? Okay, watch what happens here. Do you guys remember differences of squares when you were in algebra class? I hope so. Do you remember how to factor a difference of squares? I hope so.
Yeah.
So, you know, like a squared minus b squared factors is a plus b, a minus b. So what I'm going to do here is I'm going to go big R plus little r. That's another subscript notation. I decided to drop it, but you can use that instead. And then big R minus little r. And then I still delta theta. Okay, now I'm going to start renaming stuff. Watch closely. The difference between the radii, big radii and little radii, I'm going to rename it delta r, because it is a difference and delta means difference. And we still have the delta theta, copy it down. Now look at this right here. That is the average radius. Well, how do you know? You know when you add two things together and divide by 2, isn't that taking the average? It is. So depending on your textbook, some textbooks name this R bar, which is similar to what a statistics text names averages, or some other texts call it just simply R sub I. Okay, either way, it doesn't go away. Okay, and we still have the delta R. So I'm going to use the R sub I. I think our book uses that. So what are we saying? The area that we're trying to figure out, delta A sub I, is Ri times a difference of radii times a difference of theta. Great. So now, what if you're trying to find the volume of a solid where your capping surface was fxy? Then you would replace r with our x with the conversion, r cos, and you replace y with r sine, and then you would multiply your capping surface by the area of the base of your solid, where this difference between the two pizza slices will be your base of your solid. I know, a weird looking base. Okay, and there's the base of your solid. So you got the height here of your solid, and then you multiply it by the base of your solid, kind of like length times width times height. So then if you're going to use a double integral to calculate the volume of this weird solid, you got a generic double integral, you got your capping surface there, you got dA, and you're going to take sigma of all these little, you can think of them as prisms, and then of course you're going to take a limit, and then it's going to turn into a double integral, like that. Now this R that you see here does not go away. It is always there. I just want to do a side note. This is known as the Jacobian. And I'm not going to cover Jacobians in this class. But it would be dx d theta, dx dr. It's a determinant. dy d theta over dy dr like this. And then you would multiply these, and then you subtract those. You get a determinant where x is considered our cos and y is considered our sine. And you would take their partials. Okay, now about the R, you see this picture of a parrot? R! He's a pirate. He's a pirate parrot. And what I need you to get is that every time you see dA, when you're going to convert to polar, you don't just replace the dA with, like we did before, dy dx or dx dy when you're converting the polar. You replace dA with r dr d theta. Okay, and then you iterate your integral where you have your angle go between some range and your r go from some other range. Okay, so this right here is the area element. And from now on, I'm going to call r dr d theta the area element for polar coordinates. The area element for rectangular coordinates, this dA, ends up being dx dy or dy dx. That's the area element in rectangular. And yes, there's a difference. Yes. Don't blow this, because then you'll blow the whole thing. So now let's do the big theorem. I'm done with the derivation, and we'll do some examples. Yay! Yeah. Okay, change your variables. So when you change your variables to polar, how do you know you should even change? Well, they may tell you, like, hey, convert to polar, then integrate. Now, if you're not so lucky, here is the tip. If the region of integration is a circle or a portion of a circle or something like that looks like one of those funky polar sectors, convert to polar. Otherwise, your life is going to be hell if you try to stay in the world of the rectangular coordinate system. I'm just saying, you'll know. Okay, so you're going to have a plane region consisting of some points, and you're going to have r go between, say, g1 of theta, g2 of theta, and those might be constants. And your angle is going to go between some range of angles, and you don't want that angle to exceed 2 pi typically. And then hopefully everything is continuous. Then a double integral that's given to you like this, that probably will be given to you in rectangular, can be converted to polar. Okay, so the x's and y's get replaced with r cos theta, r sine theta, respectively. The dA, which is the area element for polar, is, be a pirate, r dr d theta. And you'll figure out what your theta range is, and then you'll hopefully figure out your range for r, and then you can hopefully integrate it. And there you go. Okay, so there's your theorem. Now let's do some examples. R, be a pirate. If you don't remember anything after graduating from my class, you will remember that. Okay. We're going to use polar coordinates to do that. And you want to, because if you try to integrate this thing without converting the polar, you would definitely need to use trig sub. And I don't want to use trig sub. Like, please don't make me. So no. Now, how do I know it's a good candidate? Well, they're telling you to convert, but you would know it. Let's sketch the region of integration first. X is going from -2 to 2. So I'm going to graph x equals 2 and x equals -2. Those are easy because those are vertical lines. Then I'm going to graph y equals 0 and y equals positive square root of 4 minus x squared. Y equals 0 is a horizontal line on the x-axis, and y equals positive square root of 4 minus x squared is the upper semicircle. That's a circle centered at the origin of radius 2. And so if I shade it in, it looks like it's going to be the upper semicircle. That's my region of integration, and it's definitely part of a circle. That tells me this is probably going to be a good candidate to convert to polar, like for reals. Okay, good news. What are the limits for r and theta? Because we're going to need to know those when we set up the double integral in polar. Well, theta looks like it's going between 0 and pi, because it's starting here at 0 and going all the way around to pi. But r, now be careful, do not have r go negative. Like I have people look at this and they think r and x are the same thing. Oh, look, we're going from -2 to 2. No. R starts at 0 and blooms outward. It starts at 0 and blooms till it gets to a 2. So not -2 to 2, 0 to 2. Okay, then what? Well, so we've got the limits for r. So now when I convert this in double integral to a double integral using polar, the x squared plus y squared is the same as r squared, but that whole thing is being raised to the 3/2. So it's r squared to the 3/2. We'll clean that up in a minute. The dy dx, that area element, what did I tell you? Be a pirate. R dr d theta. Yep. And theta goes from 0 to pi, and r goes from 0 to 2. And let's integrate this. First, some cleanup. You have to know a little bit of exponent laws. So those exponents there, do you add them, subtract, multiply, divide? What do you do when you have a power to a power? Does anybody remember?
Isn't it you multiply?
Good. Yeah, so it's r to the 2 times 3/2, but the 2's cancel, so that's going to end up being r cubed. Be careful, because we have another r there from the area element. And yes, you need to multiply all your factors of r together to get a single power of r before you're allowed to integrate. So r cubed times r is pretty easy. That's r to the 4th. Now we can integrate. Okay, great. What is the integral of r to the 4th with respect to r? Well, r to the 5th over 5, and we'll evaluate that going from 0 to 2. And we still have to integrate with respect to theta. And so that's just going to be, 2 to the 5th over 5. What is it, 25? That's 32 fifths. And then when you plug in the 0, you get 0. And so you're just going to worry about 32 fifths. Now, nothing is in the integrand, but it's understood to be a 1. So the antiderivative of 1 with respect to theta is theta. And then evaluate the theta between 0 and pi. Your final answer is 32 pi fifths. And we're done with that example. So what was the point? The point is, when you're doing double integrals, you need to know how to convert to polar coordinates because it's helpful. Okay, so here's a problem not in your course reader that I'd like you to try. And if you're viewing this at home, after you write this down, pause it and see if you can do it. So you're going to do a double integral on a dA, that's just your area element, and then in the denominator, 1 plus x squared plus y squared. And the region, they're giving it to you. They're handing it to you on a silver platter. It's all the points are theta, such that r lies between 1 and 2. Theta lies between 0 and pi. Okay? And here's a tip. You're going to convert this to polar, and it's not going to be hard. and then integrate it and see what you get. Yeah, it's going to be fun. See what happens. So the thing that you want to do is you can convert this capping surface, if you will, the integrand, to polar. Now you could put r cos theta in place of x, and then r sine theta in terms of y for the y, and that will work. But a quicker way, after you multiply it all out, is just to remember that x squared plus y squared is the same as r squared. That's always a quick fact that you can just grab. So what am I saying? I'm saying that the integrand is just 1 divided by 1 plus r squared. That's nice. Now dA, the area element, is r dr d theta. And then when you put limits here on your double integral, remember the d theta is the outermost integral. And so that the limits for the theta, I think they gave us, it was 0 to pi. That's convenient. And then the limits for r, that was nice of them. They gave it to us. Very wonderful. And now you can go integrate. And this is integrable. If you look at the integral with respect to r, you're going to use the log rule. The log rule says the integral of 1 over u du is ln absolute value of u. So you are going to use u substitution. And anytime you do that, you need to tell me the u and the du to get full credit. So good news and bad news. I already have an r and a dr in the integrand, but I need a 2. So I'm going to put one in so that I can do my u subs. I put one in provided I multiply the front of the integral by a half, and now it's legal. So now this integral does in fact look like 1 over u du, and it's going to give me the ln of what? The 1 plus r squared. And then you're going to evaluate this between 1 and 2. And I still have another integral to do, so I keep writing it. And so using the fundamental theorem, don't forget to substitute your upper limit first in place of r, and then your lower limit. And then you'll get some really weird number here. Shoot, I don't know, ln of 5 minus ln of 2. And you can condense these logs into one log using your knowledge of condensing logs from your pre-calc days. And ln of 5/2 is just a weird number. It's a constant. So you're allowed to move it out in front of your integral. It's just a constant. And now you're going to integrate a 1 essentially with respect to theta, but that's just going to give you theta. But then evaluate theta between 0 and pi. So your final answer is 1/2 ln of 5/2 times pi. A weird number there. Okay. Everybody okay with that? I'm going to do one more because this last one is a classic. You may even see this on an exam or a quiz or maybe even the final. Who knows? It's just a classic problem from Calc 3 that every Calc 3 student has to learn how to do. You don't know how to do this one, you shouldn't be graduating from Calculus 3. Sorry. Sorry to be so brutally honest, okay? What do you mean? That's not right. I know, but it is what it is. So they want us to use a double integral in rectangular coordinates. We're going to set it up. That represents the volume of this capping surface. It's a paraboloid that's actually a downward facing parabola. You could go to GeoGebra and you can graph this. And it's bounded below by the XY plane. So the base of the solid is down here in the XY plane. So we want to find the volume of this solid. That's pretty nice looking solid. So the problem is, what's the base of the solid? Because you need to figure that out, because that is going to help you iterate your double integral. Well, you'll notice it looks like your base is where the paraboloid crosses over the XY plane. So you need to figure out the trace that it makes as it crosses that XY plane. How? So the trace is found by setting z equal to 0, because z equals 0 when you're in the XY plane here. That's the whole point. So when you set z equal to 0 with the paraboloid equation and you rearrange it, aha, you get a circle. centered at the origin of radius 2. And in fact, that is the trace. So the base of your solid is this circle. And why is that important? Because when you set up the double integral representing your volume, you're going to put the capping surface in the integrand. And if we choose dy dx as our order of integration, x is going from -2 to 2. And then y, if you put your little man here, and you solve the circle equation for y, you get the upper limit is the little man's head. That's y equals positive square root of 4 minus x squared. And the little man's feet are on the bottom semicircle, which has the equation y equals negative square root of 4 minus x squared. Now, I certainly don't want to evaluate this double integral with rectangular. Why not? Because you're going to get into a trig sub problem pretty quick, and it's not going to be fun. But certainly, the first integral is going to be easy peasy. It's after you evaluate that integrand at the limits, woo boy, it's going to look nuts. So a better thing to do is convert to polar. You're going to want to do this, like for real. Like you don't want to do it, you're nuts. So the first thing I do is I rewrite the integrand by factoring out a negative from the x squared and the y squared terms. And then I convert that to polar. So 4 minus r squared is my capping surface. And then dy dx, the area element, is be a pirate, r dr d theta. And then this circle is a nice one. It's just a full complete circle. So that means theta is going to go from 0 to 2 pi. There's the whole circle. And r is blooming starting at 0. It blooms all the way out from 0 to 2. And then before you integrate, please distribute the r from the r d theta. And then this is super easy to integrate because you'll just have 2r squared minus r to the 4th over 4 and evaluate that between 0 and 2. And that's just going to give you 4. And 4 is just a constant. And then when you integrate a 1 with respect to theta, it's just theta. And theta will go from 0 to 2 pi. So your final answer is 8 pi cubic units. And that's what the solid's volume is. And that concludes the example and today's lecture. Thanks for staying. Have a happy Friday. I have office hours in 8 minutes, okay? Some folks that I've asked to stick around, I need to chat with. If you could, meet me in the Zoom office hours. All right, we'll see you.